my microphone. Is it working? Yes, it's working. Let's set this up. And we are ready. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers from the Office of Public Outreach, and it is my pleasure to welcome you here tonight. As you came in, hopefully you grabbed one of these. This is our lithograph for this evening. This is Saturn as it appeared in Hubble's image taken in 2018. And if you want to know what's special about this image, flip over on the back and you will find a few hundred words about it. One of the interesting features in this image, is right here. You see that storm here? All right, storms on Saturn are not as prevalent as they are on Jupiter. There was a storm in the northern latitudes of Saturn in 2018. And on the back, we actually show you a series of several other storms here in northern latitudes, mid-latitudes, and southern latitudes across the years that Hubble has been observing Saturn. So if you didn't get one on the way in, please grab one on the way out. Now is a pause for the cause. Please silence your phones. All right, reach in, check them, put them on airplane mode or silent, whatever you can. Thank you. Because you will not want to disrupt the talk we have tonight. Our talk is Black Holes and Gravitational Waves from Emanuele Berti from across the street in Johns Hopkins University. Coming up, we have in November, Sarah Kendrew, who works for the European Space Agency but does it so right here in our building. She did not give me an actual title yet, but she told me her topic was optical infrared telescopes, okay? So she's a great speaker. She really is a wonderful speaker. You're going to want to hear what she has to say, no matter what actual topic she uses. Because you're definitely going to want to hear what she says. In December, Serge Dieterich will be talking about red and brown dwarf, our smallest and closest substellar neighbors. What happened? We always talk about the really big things in the universe. We're going to talk about some of the tiniest stars and substars in the universe. This is going to be a lot of fun. And in January, I do not have a speaker yet because I sort of reserved this date for a possible special talk. We will be noting that we'll do it on January 14th, okay? We will delay it a week because the first week of January, a lot of people in this building will be at the American Astronomical Society meeting, so that it's always best for us to delay it a week in January so we can make sure we have a great speaker for you then. When that is set up, it will be on our website, and we have a new short link for it. It is www.stsci.edu/public-lectures. That will get you to our public lecture series page where we have links for the webcasts right here, both on YouTube and in the webcast archives, as well as our email. You can sign up for our email by putting in your email address there. We also have the list of the upcoming talks, as well as a complete list of all the previous talks. And for each of the previous talks, we have our details of it, as well as links to the STSCI webcast up here and the YouTube webcast down here. New, fancy, hopefully easy to navigate for you. All right. Our email, please, if you just use the website to sign up. If you don't like using websites to sign up, you can write it down on a piece of paper and hand it to me, and I will make sure you get signed up. If you would like to send us a comment or ask questions, you can send them to publiclecture@stsci.edu. For social media, we are available on Facebook, Twitter, YouTube, and Instagram, not just for Hubble, not just for the James Webb Space Telescope, but also for the Space Telescope Science Institute. You've got your panoply of social media channels there. If you would like to hear what I think, you can follow me on Facebook or Twitter. The observatory, the weather does look like it is permitting tonight. So the Maryland Space Grant Observatory let me know that they will be doing observing afterwards. So if you would like to go up and look through the Maryland Space Grant Observatory Telescope will collect down here after the talk. If I forget about it, somebody please remind me. Hopefully the person from Maryland Space Grant will be here, okay? If you cannot make it tonight, they also have open houses on Friday evenings. And this webpage right here shows you the observatory status. Check it on Friday afternoon/evening, and it will tell you whether or not they're going to be observing that Friday evening, all right? And now our news from the universe for October 2019. Our first story tonight, blue stragglers and the kinetic age of globular clusters. Okay, so first of all, let's parse all that because that's a lot to put together. First of all, let's start with globular clusters. This is the globular star cluster 47 Tucani, or as we call it, 47 Tuc. You know, like Friar Tuck, but 47 Tuc here. This is a ground-based image, and you can see that it's, really kind of clouded out in the center. A lot of things with ground, it's very crowded in the center of these globular clusters, and the stars all mixed together, and they're very hard to see. Who are you going to call to fix that? Of course, you're going to call Hubble. When Hubble looks at the center of that globular cluster, it can see the individual stars. And when it looked at the individual stars inside 47 Tuc, it found some blue stars that it didn't expect to see. Because globular clusters are old stars. Old stars are orange and red and yellow at the best, okay? They are not blue. Really old stars are not blue. Only young stars are blue. But yet we found some extra blue stars, nicknamed blue stragglers, as in they should be old and yellow by now, but they're still blue. So, where do these blue stragglers come from? Well, the first hypothesis, the first idea, was that they came from collisions. You take two old stars, smash them together, the hydrogen mixes throughout, you get some new nuclear fusion going on, and you can get yourself a blue star. And that's how I first learned that, blue straggler stars are collisions between stars, and you only see them in globular clusters because the density of stars in globular clusters is so great you can actually get these collisions. Well, we worked on it, and then they figured out, actually you can do an accretion method. You can actually have one star steal the atmosphere from the other star, add more in, get some fresh hydrogen, get some fresh nuclear fusion, and get the blue star again. So, but you can get these blue stars, okay? The important point about these blue stragglers is that they are blue, they're very bright, okay, and they're very luminous, okay? So they are easy to find inside globular clusters when you have a Hubble Space Telescope. Now, the dynamics, there's a second point, this kinematic age. When a globular cluster orbits all these stars orbiting around each other, you think this is a great gravitational laboratory with the stars moving all over the place. But there's an effect inside these globular clusters called dynamical friction, in which the more massive stars tend to settle toward the center, while the less massive stars get thrown out towards the periphery. So, more massive stars toward the center. These blue stragglers are more massive stars. They should congregate toward the center. We could use them to measure the dynamical age, how dynamically evolved these globular clusters are, right? So, here's how they designed a method to test this. They used the Large Magellanic Cloud, which is about 160,000 light years away, and they found a selection of globular clusters that are all basically born about the same time. So, these globular clusters are at the same distance, and they're at the same chronological age. They're about the same age. The difference between these globular clusters is their mass, their size, right? And so here is one of these globular clusters. This is a globular cluster in the Large Magellanic Cloud. This is not in our galaxy. This is in a satellite galaxy. And this is how cool how Hubble's resolution can see such great detail. And so with a selection of these globular clusters, they measured the blue stragglers and the concentration toward the center of these blue stragglers in each of these globular clusters. And for the first time, they confirmed what's probably an expected result, but that in the more massive clusters, the blue stragglers were more concentrated. They showed that you can use the concentration of the blue stragglers toward the center of a globular cluster as a measure of its dynamical age or its kinetic age of the globular cluster. Different from its chronological age, how old the stars are, how much dynamic evolution has gone on inside this cluster can be shown by these blue stragglers in the core of a globular cluster. And that was kind of cool in terms of understanding these very, very large stellar systems. Our second story for you tonight, which is, by the way, related to the litho that you got, Saturn's 2019 yearbook picture. How many of you were here last month? Okay, since you were here, you remember what we talked about? We talked about Jupiter and the OPAL, the Outer Planets Atmospheres Legacy Program, getting a gorgeous image of Jupiter for 2019. Well, if it's the Outer Planets program, if you get Jupiter, you've got to get Saturn. Boom. There is the OPAL image for 2019 of Saturn. All right. Gorgeous images of the outer planets that they take in order to study year over year the history of the outer planets' atmospheres. Now, let me grab this. Reason I gave you this here tonight is now this was the 2018 image of Saturn. This is the 2019 image of Saturn. What can we see that changed? Okay, well, here's the 2018 and back to the 2019. 2018, 2019. I go back to the 2018. What I pointed out earlier, this storm up here, right? That is gone in 2019, okay? So this storm is not very long lasting. You'll also notice the tilt of the rings, okay? If you look at the top of Jupiter, it sort of touches the rings here, but if I go back to 2018, you can see the tilt of the rings, all right? Saturn, like Earth, has an axial tilt, and that axial tilt stays constant as it orbits around the sun, but since it's moved a bit in its orbit, our view of it changes, and the perspective that we see for it changes, and now we can see less of the rings in 2019 than we could in 2018. All right, so this is yet another image in the OPAL Legacy program here in 2019, and I have a really cool fun fact for you, because Hubble has been looking at Saturn throughout its entire history. And Hubble is over 29 years old. Matter of fact, Hubble is almost 29.45 years old, which is a very important number. Yes, he knows what I'm talking about. Here's your fun fact that I'm going to leave you with. On Tuesday, October 8th, 2019, next Tuesday, Saturn will have completed exactly one orbit around the sun since the launch of Hubble on April 24th, 1990. In all the years that Hubble has been up, Saturn has made only one orbit around the sun. It has a 29.45 Earth-year orbit, which is 10,759 days. So while Hubble has been up for almost 30 years, Saturn has only had one rotation around the sun. That's a fun fact. All right, that is our news from the universe and we go to our featured speaker. Our featured speaker tonight is, is Emanuele Berti from the Johns Hopkins University. He has a storied past. Which number are you on this? Are you 4 on this? Or 4. 4, great. There we go. He has a storied past, having gotten his master's and his PhD in Italy, then having worked in Greece. Then he moved to Paris, and after the Cosmopolitan of Paris, he went to the great city of St. Louis. Left St. Louis for the Jet Propulsion Laboratory in Pasadena, and then went to the University of Mississippi, where he actually stayed for 9 years, before last summer coming here to join the faculty at Johns Hopkins University. So, ladies and gentlemen, Professor Emanuele Berti.
Thank you, Frank, and great memory. I have been to so many places I don't remember myself. Okay, so it's great to see so many people here tonight and to see so much interest in science. What I'm going to talk about tonight are the very big guys. So I'm going to be talking about black holes, big and small actually. And I will start by describing what black holes are, what the history of the black hole idea is, and then I will tell you about new ways that we have for looking at black holes and discoveries that are coming in by the day, quite literally, with the construction of gravitational wave detectors. And the first detections just started about 4 years ago, and it's a very exciting time to be alive. So what are black holes? This is an artist's impression of two black holes surrounded by accretion disks coming together and merging. This is the kind of cataclysmic event that we are observing with gravitational wave detectors. By now, black holes are pretty much accepted by astronomers as one of the many inhabitants of the universe, but there was a time when this was not so. And I will start from the very beginning. Actually, if I wanted to start from the very beginning, I should go back to a guy called Reverend Mitchell, who conceived of the idea of black holes in Newtonian gravity, but you really want Einstein gravity to describe black holes for what they really are. And so we had to start with Einstein, who in November 1915, after 10 years of struggling to put together Newtonian gravity with special relativity, came up with what we now call the general theory of relativity. So he wrote down these very complicated field equations. He presented them to the Prussian Academy of Science in November 1915, and he thought they would be very, very hard to find a solution to these equations. What he didn't expect is that a German mathematician, Karl Schwarzschild, would find a solution to the field equations under conditions of very high symmetry. So this German mathematician looked for solutions that do not depend on time and that are perfectly spherically symmetric. So, it's a mathematical solution. It is what it is. He found it while he was fighting for the German army during World War I. And at the same time, he contracted a terrible disease, and in fact, he died on the front. This solution was pretty much a mathematical curiosity at the very beginning, and Einstein himself did not believe that it described anything of physical reality, for two reasons. One was a mathematical misunderstanding. There was an apparent singularity in the equations that describe this solution. A singularity is a point where the solution goes to infinity. So at first sight, if you look at this solution, it looks like it's very badly behaved at some finite radius, and so people thought, whatever, it's mathematics, it doesn't mean much. But then there was another solution, another singularity inside, and that's a different story that I will get back to a little bit later. There's some mathematical solution of the field equations, but no one really cares. Until 1930, when an Indian student, a very gifted Indian student by the name of Subramanian Chandrasekhar, wins a scholarship to go to Cambridge and study astrophysics there. So at the time, you didn't have airplanes, so this guy gets on a boat and he travels for about a month to go from India to Cambridge, and on the boat he's doing math. He's doing what he knows how to do, and he's tinkering with ideas coming from quantum mechanics, that at the time was a brand new theory, and special relativity, and he understands that certain stars that are called white dwarfs must collapse gravitationally if they are more massive than a certain mass, which is 1.4 times the mass of the sun, what we now call the Chandrasekhar mass. So he gets to Cambridge and he talks to Sir Arthur Eddington, who at the time was the British royal astronomer. So he was the world leading authority in astronomy. And Eddington, in public, ridicules his discovery, and he calls it a stellar buffoonery. And Chandrasekhar was a young kid at the time. He's completely shattered by the reaction by Eddington, and he decides to leave. And he goes to the United States. He moves to Chicago. He becomes a professor in Chicago. He works for many, many years, makes a lot of discoveries, writes 7 books. And in 1983, he gets a Nobel Prize for what we now understand was the discovery that these stars, when they are too massive, must collapse. Okay? Then, in 1939, something else happens. In 1939, of course, the Second World War begins. And at that time, there's another very brilliant physicist in the US who goes by the name of Robert Oppenheimer, and I'm pretty sure that several of you have heard that name before, who's working with a student, Snyder, on this idea of collapse. And basically, he understands in a paper that is now famous, but at the time went unnoticed, that stars can collapse and form what we now call black holes. But this idea goes dormant because of history. Oppenheimer basically has to stop working on fancy astrophysics, and he goes to Los Alamos, puts together a group of brilliant people, and builds the atomic bomb, right? At the same time, there's another guy who's a main actor in this story who's called John Wheeler. John Wheeler went to Denmark, where he studied with Niels Bohr. I was recently there visiting the Niels Bohr Institute in Copenhagen, and there's some nice pictures of John Wheeler. You see him here. He had a very special style when he lectured, and he used to draw a lot of diagrams on the board and then go through the diagrams one by one during his talks. He was a very fascinating speaker. Wheeler was a nuclear physicist by training. So he studies with Niels Bohr, and then a tragedy happens. His brother dies in my native Italy while fighting in World War II. And at that point, he decides that he really wants to get involved in the Manhattan projects. He joins Oppenheimer, works on the atomic bomb. You know how that particular story ends. The war ends in 1950. Wheeler decides to get together with many brilliant students. One of them is this guy, Kip Thorne, who got the Nobel Prize just a couple of years ago. And he returns to the problem of gravitational collapse that Oppenheimer had attacked back in the 1930s. And with this group of students, he understands gravitational collapse much better. And in 1973, he writes this book called Gravitation that is like 1,000 pages thick, and I have 2 copies of the book in my office, and that's how revered it is, and it's the Bible for everything gravitation. Okay. Then the 1960s. In the 1960s, there's a couple of crucial developments. One is that, once again, a mathematician springs to action. This guy is called Roy Kerr. And I told you that the solution that Schwarzschild had found was very symmetric. It was perfectly spherical, and we know that stars rotate. So, you know, if a star collapses, it cannot form an object that is not rotating because of conservation of angular momentum. And this guy, Kerr, finds a solution that is what we call now a black hole, and it's rotating. So that's the mathematical progress. And by coincidence, in 1963, there is an astronomer at Caltech called Martin Schmidt, who discovers an object that is extremely bright, very far away, located at a redshift of 0.15, and changes. It changes on a timescale that is very short. So he calls this object a quasar, a quasi-star. This object has to be very bright, very compact, and it outshines even the brightest galaxies. Now we understand that that object was the first supermassive black hole. So in the 60s and 70s, many other things happen. One of them is developments that involve the Space Telescope that I will tell you about in a minute. And Kip Thorne, Wheeler's student, gets together with another bunch of very brilliant students, and they try to understand whether these black hole solutions are stable or not. They are still purely mathematical solutions, so people want to understand if they make sense at all, and they try to understand if they're stable, and they had to do a lot of math, and the math turns out right, and these objects are stable. Okay? All right. Not only they are stable, they're very fascinating. And they're very fascinating because 2 British mathematicians, one of them is Roger Penrose and the other one is Stephen Hawking, they discovered that the gravitational collapse that I spoke about before is a very generic feature. And whenever it happens within the theory of general relativity, it inevitably leads to the formation of singularities. Now, this is not the fake mathematical singularity that I was talking about before. It's a real singularity. So black holes are sort of like the time reversal of what happens in the birth of the universe. At the birth of the universe, there's a singularity, or a point at which we don't know what the laws of physics look like, and everything expands out of the singularity. Gravitational collapse is basically the same film in reverse, all right? And so Hawking in particular understands this fact, and he also understands something else, that if you try to combine quantum mechanics with black holes, then black holes are not quite as black as they're pictured to be, because they can radiate. Now we call that Hawking radiation. We think that it holds clues to the nature of quantum gravity that we don't understand yet. So, all in all, black holes are mathematical solutions of the Einstein equations. They do not involve matter. They're very pretty mathematical constructs that I can write down in 2 lines on a piece of paper. But they are extremely fascinating because, as Chandra said, and Chandra is someone who has had a very active scientific life, in all of that scientific life extending over 45 years, the most shattering experience for him had been the realization that an exact solution of Einstein's equations discovered by Roy Kerr provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. This shattering before the beautiful, this incredible fact that a discovery motivated by a search after the beautiful in mathematics should find its exact replica in nature, persuades me to say that beauty is that to which the human mind responds at its deepest and most profound. It's mind-boggling for someone like me who does physics for a living that you can write down simple equations and solve them, and the universe works that way. You know, it's really amazing. So how do these black holes get there in the universe? In several ways, we think, but the most likely way is through the collapse of stars. So what you have are stars. You guys probably come here often. You know how stars work. Stars work through a balance of gravity and pressure forces. Gravity pulls stuff in. When stuff gets compressed, it becomes hot. It becomes hot, there are nuclear reactions. Those nuclear reactions burn, typically, 2 hydrogen atoms into helium and release some energy, and that energy generates pressure that pushes outwards, okay? So you have nuclear reactions, you burn nuclear fuel, you push outwards, gravity pushes inwards. And when stuff becomes more and more compact, there are other nuclear reactions that come into play. So you have hydrogen that burns into helium, and then carbon, and then neon, oxygen, silica, and iron. And that's it. And that's it because iron, out of all nuclear elements, is the one that has the lowest binding energy per nucleon, we say. So it's the most stable of all nuclear elements. You cannot make anything that is more stable than iron. Okay, so when you run out of fuel, what happens? Gravity wins. And when gravity wins, all of this stuff collapses and the star dies. And it makes a big splash and it produces what we call a supernova. The first supernova was observed by Chinese astronomers back in 1054. And what they saw was they were looking at the sky, they were keeping very careful record of everything that they saw. And in their journals, they wrote down that a star suddenly appeared in the sky. It was there for about 23 days, and then it disappeared. So they didn't know where it went. And now we understand that this was a supernova, and what was left behind was what we now call a neutron star. What are all of these crazy things that I'm talking about? White dwarfs, neutron stars, black holes. I like zombie movies, and I hope you like this movie too. It's brilliant. It's brilliant. This is The Night of the Living Dead. If you haven't seen it, I highly recommend it. What these objects are, they're zombies. They are stars who died and come back to life, okay? How do they come back to life? There are several different ways that stars can come back to life. When a star is small, smaller than about 3 solar masses, take these numbers with a grain of salt because no one really knows, but let's say smaller than about 3 solar masses, then a star like our sun, after it burns its nuclear fuel, it expands, it becomes a red giant, then it collapses eventually, and it forms a white dwarf. If the mass of the star is higher, how much higher? Between about 3 and 10 solar masses, about, okay? Then When the star collapses, it forms what we call a neutron star. But if the star is really, really massive, more than about 10 solar masses, then there is nothing to keep it from collapsing, and it produces a black hole. What keeps a white dwarf together is quantum mechanics. It's the uncertainty principle. It's actually the Pauli exclusion principle between electrons. So electrons don't want to be together and they push outward. What keeps a neutron star together is the same idea, but for neutrons. And what keeps a black hole together is nothing. A black hole is just stuff that keeps collapsing. Okay? So if you imagine picturing gravity as the bending in the fabric of space-time, what you can imagine is that you have a large sheet, and this sheet is only mildly bent by the sun. It's much more bent around a white dwarf and extremely bent around a black hole. And the way to understand the gravitational collapse that I was talking about before, a very useful analogy comes from a book that Kip Thorne wrote, which is called Black Holes, Time Warps, Black Holes and Time Warps, I think, Einstein's Outrageous Legacy. This is what he calls the parable of the ants. So imagine that you have a bunch of ants living on a membrane, like the one that I was talking about before. And one of these ants is a loner. She's an astronomer. She decides to stay at the side of the membrane because she doesn't like partying. But the other ants, they decide to congregate at the center and have some drinks. So they go to the center, and the membrane, under the weight of the ants, starts collapsing, okay? Now, these ants decide to communicate with the loner by sending little balls, okay? And they send little balls every 1 second, let's say. So they send a ball, and they send a ball, and they send a ball, but at the same time as they're sending balls, they keep falling because the membrane is collapsing down. And at some point, the speed at which the membrane is falling down is faster than the speed of the balls that they're throwing out. So in this analogy, the balls are light, and the fact that the ants are congregating at the center and collapsing is matter in a star that is collapsing to a black hole. And at some point, as you can imagine, there's a horizon, there's a point beyond which these balls will never get to the astronomer anymore, and he will think that these ants are frozen at that point. And in fact, initially, people thought of black holes as frozen stars. That's what they were called in Russian books before John Wheeler and the gang came over and started calling them black holes. So this is exactly what happens during gravitational collapse. From the point of view of the ants, nothing wrong happened. They just fell in and they got trapped. They'll die, but whatever. That's life. So you cannot see a black hole because by definition, not even light can get out. So how do we see black holes? The way we see black holes is through gas that is accreting onto the black hole. And that's because physics tells us that neutron stars can never be more massive than about 3 solar masses. There's just no way that regular matter can keep them together if they are more massive than that. So you watch gas that is falling onto something that is very compact, and if it's very compact and it's more massive than 3 solar masses, then you can be pretty certain it's a black hole. This is the way the first black hole was observed. In 1964, by this guy, Riccardo Giacconi, who comes like me from Italy and got the Nobel Prize, unlike me. And he was here, and he played a major role in the development of the Space Telescope, as you all know. And Giacconi went on, and he basically created a whole new way of looking at astronomical objects through X-rays. There's a second way that we can look at black holes, and I'll show you a neat movie here. This is not a black hole that is born from the collapse of stars. This is what the monster that lives at the center of our own Milky Way. It's called Sagittarius A star, and the way we see it is through the motion of S stars that are very close to that central object. This white dot is only there to guide the eye. It's not really there. And what we observe over time, you can see the date of the observations over here, are perfect ellipses around something that we don't see. Now, from the shape of those ellipses, you can tell the mass of the big guy that they're orbiting around. And because these stars are so close, you can also tell that that object has to be very, very compact. so compact that the only reasonable explanation is that it's a black hole. And we can measure the mass of the black hole now very accurately, and it's 4 million solar masses. How they get there? We don't really know, and we want to find out, and I'll tell you some ideas that we have to find out. Now, everything that we have seen in astronomy so far, we have seen it through electromagnetic waves. Electromagnetic waves are basically light of different frequencies, right? And I find this image really fascinating. This is Andromeda M31, which is very, very close by as far as astronomical distances go. And you can see it in the visible. This is what you could see if you had a very powerful optical telescope. But you can also see that if you look at it in different wavebands, it looks very, very different. You're seeing very different physics and very different phenomena going on. For example, here what you see are dust lanes. What you see up here is what the galaxy looks like in X-rays, and you can see that there's a lot going on at the center. And we now know that so much is going on at the center because there's a massive black hole there. But you also see a lot of stuff going on out here, and those are supernova explosions and stuff like that, very violent phenomena that you would never see in the optical. And what I find most fascinating is the radio observation. Can any of you tell me what those red dots are? You know? So those are quasars. Those are other black holes that are behind the galaxy, but they're so bright that they outshine the galaxy, like I told you before. So you see many, many black holes in the picture there. Huh? Okay, now to explain a little more about how black holes work, I have to introduce a little bit of general relativity. And I need to explain how general relativity is different from Newtonian gravity. Newtonian gravity is a perfectly good theory. I just spent about a month over the street there at the physics department teaching only Newtonian gravity. It's super beautiful and explains everything that you need to know about gravity in the solar system, except maybe one thing, but that's kind of minor. And Newtonian gravity works in the way that I bet most of you know. It tells you that two objects attract each other with a force law that is proportional to the masses of the two objects and inversely proportional to the square of the distance. Now, that force law is very beautiful, pretty accurate, but it's wrong. And it's wrong because it tells you that the interaction between two masses propagates at infinite speed. And because of special relativity, we know that nothing can propagate faster than the speed of light. So when Einstein discovered special relativity, he spent about 10 years thinking long and hard about how to fix Newtonian gravity so that it wouldn't clash with special relativity. And he came up with this crazy idea that gravity is not a force at all. So gravity is the natural state of motion of objects. The only reason I'm not falling through the floor is that the floor is pushing up on me. If there were no forces from the floor pushing up on me, I would be happily falling. And that's the natural state of all things. They just fall all the time, okay? So this is summarized by another famous phrase by John Wheeler, which says that space-time tells matter how to move, and mass tells space-time how to curve. How do we know that Einstein was right and Newton was wrong? The first time we found out was exactly 100 years ago. There was a very famous expedition led by Eddington, the same Eddington that I was talking about before, the royal astronomer, the one who ridiculed Chandrasekhar, who knew that there would be a complete solar eclipse, and he knew where that solar eclipse would happen. So he set up an expedition. He himself went to a small island close to Africa, the island of Príncipe, and he sent other astronomers to Sobral in Brazil, in the Amazon region of Brazil, and they observed what happened during the solar eclipse. Why were they interested in this? Because one of the predictions of Einstein's relativity is that every mass must bend light, okay? So they knew that if they would look at the spot where the sun was, because the sun was there, and because it was dark, they could look at the positions of the stars behind the sun and measured how deflected they were because they were behind the sun. And Newton predicts a certain deflection. Einstein predicts exactly twice as much. So they went and they looked at the position of all of these stars during the full eclipse. They had 2 different observations into different places just to make sure that they got things right. And they found that Einstein was right and Newton was wrong. And then the next day, newspapers, never trust the newspapers, they came out with things like lights all askew in the heavens, men of science more or less agog over results of eclipse observations, Einstein triumphs, stars not where they seemed or were calculated to be, but nobody need worry. Okay? Don't worry, don't worry. Now, we have seen that light bending in a much more spectacular way, and I'm sure all of you have seen this picture. This is the same light bending, but it's the much more extreme bending that happens around a black hole. Now, if I were living around a black hole, I could see the back of my head and discover how bald I became over time. Because light can form, the gravity around a black hole is so strong that gravity can go around in circles. And those circles are called light rings. And this is pretty much what you're seeing here. Okay, this is a light ring. It's beautiful. But it's still an observation in the electromagnetic spectrum. Why am I here tonight? To tell you that there's a new way to look at black holes that is completely different, and it's based on gravitational waves. What are these gravitational waves? Well, they are very different from electromagnetic waves to begin with. Everything that you look at in your daily life can be described by electromagnetic phenomena. And if you look at the typical wavelengths of those phenomena, stuff that you see with your own eyes is in the optical. It's over here. It's a pretty limited band. Then you have the gammas, the X-rays, the ultraviolet, infrared, the radio down here, all of those beautiful images of Andromeda I've shown you before. And that's one sense, right? One sense that we have to look at the universe. Gravitational waves are bending in space-time, and they propagate at frequencies that are very different. In fact, if we had to understand them in terms of senses, their frequencies are so low that they are more similar to sound waves. Sound waves are compression and rarefaction of air that we pick up with our ears, and they have frequencies that are very low compared to all of the electromagnetic spectrum. Now, I'm not saying that gravitational waves are sound, but you can think of them as a completely different sense that you have to look at the universe, that is more like hearing than it is like seeing, okay? And what are they? So gravitational waves, you can understand them pretty much as tidal gravity. So when the moon goes around the Earth, it exerts tides, and those tides produce the effects that you see on oceans, for example. If you imagine that a gravitational wave goes through me in this direction, so you are sending a gravitational wave my way, what the gravitational wave does as it passes through me is it makes me thinner and taller and a little bit happier, and shorter and fatter and a little bit sadder. And it does so every time it goes through, okay? So by how much? Not very much happier, not very much sadder, because the typical displacement, so if you imagine that you had a gravitational wave generator that you could put in this room, well, the best you can do to generate gravitational waves is, say, take 1 ton of stuff and make it spin as fast as you can. And if you look at the typical deformation that the gravitational wave would produce on me, it's 1 part in 10 to the 39. Okay, not very much happier. So there's no hope that we can generate gravitational waves on Earth and detect them. But if you start talking about massive black holes in the universe moving at speeds close to the speed of light, you get a number that is still ridiculously small. It's about 10 to the minus 21. That is still ridiculously small. So if I want to build a detector on Earth, I need to make it as big as I can, because I want to make it long, because that number is the delta L over L. It's the fractional displacement as the wave goes by. And even if I build a detector that is like 1 kilometer long, that fractional deviation is still going to be much smaller than the nucleus of an atom. So about 20 years ago, when I started studying this stuff, the other physics students in my department were making fun of me. They're like, you understand how crazy all of this is? And they were right. So it took about 20 years to actually get there, but eventually we got there. And the way we got there is by building what is called a laser interferometer. And the idea here is that you basically have a long pipe where you make vacuum, you make the best vacuum you can make, then you shine a laser here. This laser is split into two rays at something called a beam splitter. This is a semi-transparent mirror. So some of the laser goes up, some of the laser goes this way, and then you put two big mirrors at the end of each arm, and those mirrors reflect the light back. Now, if there is no gravitational wave passing by, there's a photodetector here, and it sees that the light coming from the two arms interferes destructively, and so you see black. You don't see anything, okay? But if there is even a tiny displacement in each of those arms, then you don't see black anymore. And interferometry is a very, very precise way of detecting even the tiniest vibrations. This was Ray Weiss's idea and the one for which he got the Nobel Prize. Now, how big do you need to make those pipes? This big. So this thing is close to Mississippi, where I used to be. This is actually in Livingston, Louisiana. It's beautiful, except that there's a lot of crocodiles, alligators over there. It's a nice place. I took pictures over there. And the beam splitter and the photodetector are housed in this white building over here. The light goes all the way down, almost, you see, almost all the way to the horizon. And you cannot fit this in a single picture. So, you know, the other arm keeps going over there, somewhere over there. And this is the one in Livingston, Louisiana. There's another one that they built in Hanford, and well, used to be a nuclear site. And then there's another one that they built in Italy. You can tell that the scenery is pretty different. It's close to where I was born. And it's called Virgo. It was built. It's an Italian-French collaboration with other contributions. So, okay, so what happened? These things turned on. Actually, the two LIGOs turned on. The Italians are slower. And what happened is that in 2015, I started hearing rumors that something happened, okay? I'm not part of the LIGO collaboration, but I know many people. And then around February, I got an email from one of the editors of Physical Review Letters, that is one of the main physics journals, telling me, we got a paper that has a pretty big discovery. Would you like to write a popular article to explain what happens? Of course, I had heard something, and I didn't sleep for a few days until I actually got my hands on that paper. And then I wrote this thing here, and this is what they saw. So what you see here is two black holes coming together. As they come together, they spiral faster and faster because they're producing gravitational waves. The signal is a maximum, and then these two black holes merge. They form a single black hole, and that black hole wants to become a simple rotating black hole of the kind that Kerr wrote down in one line of math. And when it does so, it rings down. We call it ring down because it's the same thing that happens when you hit a bell with a hammer. It wants to vibrate away all of the deformations, and it does it by producing a sound, and then it becomes the bell that it used to be before, by ringing down. Okay? And here, I'm gonna make you hear the sound that those two black holes made when they merged together. You're gonna hear it twice. The first is the actual sound. If you take the gravitational waves and you sonorize them, that's what you would actually hear, and it sounds like a pop. It will sound, well, you'll hear it. And then they slightly change the frequency so that you hear the initial part of the signal a little better. So I'll play it. So the thud that you hear, that's this ring down signal. And then they expanded the frequency band so that you can hear it better. You can hear what we call a chirp. It sounds like a whoosh more than a chirp. But it's pretty much the same way that birds make sound. It's a sound of increasing frequency and increasing amplitude. So it's the same kind of sound. It depends on the frequency at which you play, but it's pretty much the same thing that birds do. Black holes sing, right? Okay, so this thing is published. They put in nominations for the Nobel Prize a little too late, so they don't get it the first year around, they get it the next year, because this was such a big deal. And the people who got the Nobel Prize are Ray Weiss, who basically invented the idea behind the interferometers, Kip Thorne, that I nominated many, many times, and Barry Barish, who basically put together the collaboration and made it work as a particle physics experiment. 1,000 people worked on this. So, what happened afterwards? What happened is that besides those two detectors, notice that they turned on September 12th. 2 days later, they detected something. So all of a sudden, we became just sensitive enough that we could see these things. And we knew at that point, we knew that we would see more. Okay? In fact, we have seen many more. The detectors were operational for a little while. You see from December until January. Then they turned on for an upgrade, and then they started taking data again. And they saw a total of 10 binary black hole mergers and 1 neutron star merger, one merger of 2 neutron stars. And you can go now and look at these events as they are being observed day by day if you go to that website at the bottom, because it's open science now. Every time one of these things happens, an alert is sent out to astronomers who can go and look for electromagnetic radiation produced when these cataclysmic events happen. This is the catalog of the 10 events which are public and published. There's 10 black holes, and then there is one that is much longer. That's the merger of 2 neutron stars. Why was that so relevant? I will explain it in a minute. So, think again about the way that a gravitational wave works. It goes through me and it makes me a little taller, and then a little fatter, and a little taller, and a little fatter. Now, I built a detector, which is 2 arms. So if a gravitational wave comes in and it hits the detector face on from above or below, it's going to stretch and squeeze both of the arms, right? But if it comes from the side, it's going to stretch and squeeze only one of the arms. So you would expect that these detectors are going to be a little more sensitive, see a little farther up, or farther out in the universe if the waves come from above or below, and they're going to be less sensitive if the waves come from the side, right? So this is pictured in this peanut here. This is the sensitivity of the detector to gravitational waves at different positions in the sky. It's more sensitive up and down and less sensitive on the sides, okay? So what this tells you is that a single gravitational wave detector is not very good at locating things in the sky. It's basically an omnidirectional detector. So if I want to know where these waves are coming from, I need at least 2 detectors. Why? Because if I have 2 detectors, I can tell from the time that the waves arrive at one detector and the other that these waves travel at the speed of light. So I construct 2 spheres that travel at the speed of light around those 2 detectors, and 2 spheres intersect in a circle. So if I have 2 detectors, I can locate the source in the sky on a ring, okay? It gets even better if I have 3 detectors, because if I have 3 detectors, now I can take the intersection of 2 rings, and I have 2 points in the sky. So with 2 detectors, you locate the source on a ring by time of arrival. With 3 detectors, you can tell that it's either this point or the point opposite in the sky. So this is exactly what happened with the binary neutron star. They had 3 detectors because the detection happened in August when the Italian detector finally woke up. So the 2 LIGOs saw a signal. The Italian detector, unlucky that we are, didn't see anything. But it didn't see anything because the waves, unfortunately for the Italians, were produced in the blind spot of the Italian detector. So we knew, because it didn't see them, that it had to be in a certain location in the sky. And from that, we could locate the position within almost 2 points. They don't quite look like points, okay? There's experimental error. But then something miraculous happened, that at the same time, Fermi, an observatory to look for gamma ray bursts, observed a gamma ray burst. Just a little delayed from the gravitational wave signal. And by combining these 2 things, we could locate the source in the sky into a very tiny region. And at that point, the hunt was on. Every single astronomer on Earth, more than 3,000 astronomers, pointed everything they had at the spot in the sky. And so they started seeing fireworks. They saw optical, they saw everything. They saw everything, okay? That was amazing. It never happened again. We were super lucky. There's people who say that the L in LIGO stands for lucky, because the first binary black hole that we saw was super loud, and it happened 2 days after they turned it on. And the first binary neutron star, we located it in the sky super precisely. Now we can use these observations to do cosmology. That's amazing. I don't have too much time to explain it. Maybe you heard in previous talks that there is a tension in cosmology now between measurements that are made with the microwave background radiation, cosmic microwave background, and measurements that are made locally by people like Adam Rees, who work here. They get different numbers for the expansion rate as measured by a quantity that is called the Hubble constant, okay? And gravitational waves are not quite precise enough to say who is right, because the measurement of the Hubble constant that they make has errors that are large enough that they're compatible with both measurements, but we hope that in the near future they will help us understand how the universe expands. What else happened? These detectors went on again in April of 2019. I don't know why they chose April 1st. It's a very bad date. And after they turned on, they started recording events on a very regular basis. So regular that my slides are always outdated. So I don't know, if some of you came here early, I had 28 here. I had to write 31 because I gave a similar talk like last week for a high school in Italy, and there were less. You know, they keep coming, they keep coming. It's super exciting. Every morning I have an app on my phone, and I look at the app and it tells me, there's a new event today. Great, it's a binary black hole, it's a binary neutron star, you know. So what are we doing now? We're building more detectors, because the more detectors we have, the better we can localize sources in the sky. So now we have 2 LIGOs, we have Virgo in Italy. This is a prototype that is not sensitive enough to see things. There's a new detector. The Japanese were super fast. They built a detector underground in the Kamioka mine, and it's called Kagra. This is gonna start taking data before the end of 2003, the 3rd observational run. And the Indians are also rushing to build their own detectors. They're gonna get a LIGO shipped all the way from the US, and they have a site where they started making these giant vacuum holes. And what's gonna happen when LIGO India goes online is that we're gonna have a network that is spread throughout the Earth. That's the way that they took that picture of the supermassive black hole, by having very many observatories all around the Earth. And we're trying to do the same with gravitational wave detectors, so we can locate the sources in the sky better and go after the electromagnetic counterparts. And like I said, you can go online. You see, I took a screenshot of this website on 1909-24, but now there are more. They keep coming. There's more and more events. And you can go online and you can see what's happening by yourselves. How much time do I have? I can 5-10 minutes, okay. I want to tell you something about what we understood from these first detections. First of all, we understood, we can now pin down more precisely how often these objects merge in the universe. We have a pretty good idea now of how often black holes merge. We have a not so good idea of how often neutron stars merge, but that's getting better. And at the end of 2003, they're going to have a much better measurement of the rate. At the end of the first 2 observing runs, we had not observed any neutron star black hole, so we could only place upper limits on how often they merge in the universe. But now the rumor is that they have seen some. And so by the end of 2003, we will know more or less how often black holes merge with neutron stars in the universe. There is also some evidence that the rate at which things merge in the universe changes with the age of the universe. And that makes sense because these things are made out of stars. So more or less they should follow the star formation rate. The more stars you form, the more black holes you form. So we expect that the black hole merger rate should peak at some distance and then go down. Because when the universe was very old, we were not making stars, right? The other thing that we understood is that the masses of these guys that we are observing are very different from the masses we estimated before. If you remember, I told you that to estimate black hole masses, we looked at gas falling onto black holes. And from the orbit of the gas, we can tell how massive the black holes are. And those are the purple dots that you see here. Now you can see that all of the black holes that LIGO saw seem to be more massive than that. So one question is, how do you make them, right? Most people now believe that these black holes were formed when the universe was a little bit older and the metallicity was lower. And the reason is that the metallicity is the fraction of heavy metals that you have in a star. Heavy for an astronomer is everything heavier than helium. So anything that is not hydrogen or helium, astronomers here call it a metal. Don't blame it on me. But so if a star has more metals, then winds are not as efficient at blowing stuff out when a supernova happens, and so more mass falls in, and so the black holes that you form are more massive. And so we think that's what happened. But there are other people that believe that these black holes are so massive because they are formed in clusters of the kind that Frank was talking about before my talk. So there could be very dense environments where these black holes, through dynamical friction that he was talking about, fall toward the center. If you have many black holes and they're close to each other, they can bind. And when they bind, they can merge. And so maybe what's happening is that these black holes are not first generation. They are not born from a star. They're not zombies of the kind I was talking about before, but they are zombies merging with each other. So they are second generation mergers. Okay, so the masses, I already said it. One thing that is fascinating is that we don't see black holes more massive, at least so far. I hear rumors that maybe this is going to change. But we haven't seen any black holes more massive than about 40, 50 solar masses. And that's very interesting because there is something in astrophysics called peri-instability supernovas. So when a supernova happens, you can have collisions between gamma rays and nuclei that produce electrons and protons. Now, those are pairs, electron-proton pairs. When that happens, there's a sudden drop in pressure in the stuff that is contained within your supernova. And so the material suddenly collapses toward the center. And you have a big blowout of stuff, and nothing ends up collapsing into the black hole. For this to happen, you need to have stars that are more massive than about 130 solar masses. So this tells you that the remnant of that supernova explosion cannot be more massive than about 50 solar masses. Lo and behold, all of the first observations tell you that the pre-merger black holes do not seem to be more massive than 50. So maybe we're understanding that this peri-instability supernova actually happens. But if we see black holes that are more massive than that, then astronomers will have to scratch their heads again and find ways to make black holes that are more massive than 50. Okay? And I'm sure that they will. I'm sure that they will. Okay, this is ideas that I already spoke about. Let me tell you something a little fancier. One thing that we really want to see is spins, for reasons that I don't want to explain right now. You can ask me later. Another thing that we want to understand is whether the stuff we are seeing are actually black holes. And one way that we can do it is through what we call black hole spectroscopy. I told you many times already, these black holes are very, very simple. And we can think of them as the atoms of gravity. Now, ordinary atoms have spectral lines, right? And the way that we identify elements in the universe is by looking at the spectral lines. Now, the black holes that are produced through these violent mergers, if they are the black holes of general relativity, they also have gravitational spectral lines. And we can compute them all. And because black holes are so simple, all of those spectral lines depend only on the mass and the spin of the black hole. So, LIGO has seen things that seem to be very compatible with general relativity, but it was not quite precise enough to measure the frequency of the stuff at the end over here. Because as you can see, there's a lot of noise here. What we see is perfectly compatible with the predictions of general relativity, but as our detectors become more and more precise, we will be able to measure those frequencies and do spectroscopy, gravitational spectroscopy with black holes. Let me skip to what's next. What's next are more sensitive detectors on Earth and detectors that can look at other wave bands, just like radio astronomy is looking at other bands in the electromagnetic spectrum. We want to look at other bands in the gravitational wave spectrum. So what we're doing now is the Europeans, together with NASA, are planning to put one interferometer of the kind that I was talking about before in space. This is the reason I moved to the United States. That's why I went from Paris to St. Louis, and I was perfectly happy to do it. And so the idea that led me over here was we are going to take 3 satellites, we're going to launch them in space, they will make an equilateral triangle. This equilateral triangle will trail the Earth in its orbit around the sun. It sounds like science fiction, right? But that's what the other students told me when I spoke to them about LIGO when it happened. So we're going to put 3 satellites in orbit. They will cartwheel behind the Earth going around the sun. And as a gravitational wave passes by, it will now stretch and squeeze the triangle. So we're going to shoot lasers in between the different satellites, measure the arrival times, and if a gravitational wave passes by, bingo, the distance between the satellites has to change. Okay, that's the idea. Now, with those things, you can see not stellar mass black holes merging, but supermassive black holes merging. Stuff like the one at the center of our own galaxy. We think that those black holes got there because galaxies like to merge with each other throughout the history of the universe. And so by measuring how those massive black holes merged, we can tell how the galaxies came together. And that's the real goal. That's why I moved to the US. I like Italy, but now I go back for holidays. So there was a prototype mission that launched in December 2015 that showed that we can actually do this, that it's feasible. These are technical details that I can tell you about later. And we want to do spectroscopy in space. And there's even a hope that we could detect dark matter around black holes in this way. I want to leave you with one plot that was made. So I came to the United States. I went to JPL Caltech, and I met an aerospace engineer over there who is now my wife. And the guy who was my witness at the wedding is this guy, Steve Drasko, who made this movie. And that's a long-winded way to say that a friend of mine made this. So what you see in this movie is a stellar mass black hole that falls into a massive black hole. This is one of the things that we want to target with LISA. And why is it fascinating? What you're going to see here is the orbit that the small black hole makes around the big black hole, and you will hear the gravitational waves at the same time, and they will sound much more interesting than the whoop that we heard before. So let me play it. Notice also that this object is falling in. So my friend had to zoom in with the camera as the object falls in. Let me play this if I can. Where is it? Where is The applause is for Steve, okay? Now, you understand that there's a lot of structure in those gravity waves. and you can tell very precisely from those gravitational waves what the central black hole looks like. In fact, one of the ideas that we're pursuing now is that if there is dark matter around that black hole, by measuring those waves, you could tell what kind of dark matter could be around that black hole. Okay, that's just a sketch. I want to leave you with a couple of suggestions for reading. One is this beautiful book by Kip on the history of gravitational waves. You will see that he's the optimist who pushed many of us to work in this field, because there is a book from the 90s, and he said, we're going to see them within 10 years. That's when I was a student. He was lying to me. The one over here is the autobiography of John Wheeler that is really fascinating reading. That's all. Thank you.
Okay, I'm sure we have a bunch of questions. We had many of them online. Who's got the first question for our speaker? All right, try in the back.
Now the fun part. Ready?
Good catch.
Okay, so I was going to ask, what is quantum foam?
You know, I always get that question. So quantum foam, John Wheeler had a thing for names. He named a lot of things. A black hole comes from him. Geon is something else that comes from him. A geon is mass without mass. At some point, so I told you before that one of the disturbing predictions of general relativity, according to Penrose, is that if you make stuff collapse, it will create a singularity at the center. We don't like singularities. We don't like singularities. It means that the equations are going bad. We think that just like Newton's theory was incomplete, so also general relativity is incomplete. And what happens is that when the curvature of space-time becomes very large but not quite infinite, there have to be some quantum corrections that come in. Now, there are some theories, like loop quantum gravity or string theory, that make the same predictions as general relativity for relatively low curvatures, and they make different predictions when the curvatures become, we say, Planckian, close to the maximum curvature that we can expect. And so the way that Wheeler liked to think about this in his visionary way is that the topology of space-time, the way that the sheet of space-time bends, becomes foamy when you get close to that singularity. And so you could have defects in space-time that produce things like wormholes, and all of this is a lot of blah blah, and I can do it here, but we don't really know what happens. Okay, that's the truth. That's the honest truth.
Okay, I have a question from online first. They were a little confused by when you were talking about needing space observatories to see supermassive black holes. Wouldn't there, basically, it says something like, I'm assuming the size of the black hole determines the strength size of the gravitational wave.
That is right.
So why would you need bigger things to see the bigger ones?
You need big detectors. Okay, so first of all, the size of the detector is basically proportional to the wavelength of the gravitational waves that you see. So the longer the detector, the longer the wavelength, the smaller the frequency. So if you want to see small frequencies, you need to build very big detectors. Why can you not do it on Earth? So you can build bigger detectors on Earth. In fact, one of the ideas here in the US to build a better LIGO is to make it, instead of 4 kilometers, 3 miles, I'm sorry, I'm in the US. Instead of 4 kilometers, you want to make it 40 kilometers, okay? What's the problem? That if you want to make something that is 40 kilometers long, you better start digging, because the Earth is not flat. We agree on this, right? So you need a lot of digging, whatever those people say. And besides, there's another problem that is more serious. The Earth, there's earthquakes, unfortunately, and there's seismic motion. Now, these detectors now are so sensitive that the main limitation comes from the uncertainty principle. That's how sensitive they are, okay? Quantum mechanics of the movement of the mirrors is what we have to take into account now. At low frequencies, there's no way that you can beat seismic noise, the noise that is caused by the fact that the Earth is shaking. So there are some ideas to improve on that, build them underground. You have to dig a lot. And in any case, you cannot make them sensitive at frequencies below, let's say, maybe 1 hertz or so. So if you want to build something that is sensitive below 1 hertz, you need to go to space, because there's no earthquakes in space. So you build satellites and you make them as large as you want.
Okay.
What's the consensus on primordial black holes?
Oh, is there a consensus? I have a lot of friends on the other side of the street that work on primordial black holes. They're very fascinating. So they are interesting because they could be very, very small, and so Hawking evaporation could happen on shorter time scales. They could and probably were formed in the early universe. The question is, do they make a fraction of the dark matter? Can we see them? When the first detection happened, people like Mark Kamionkowski and the students over there got really excited because, like I told you before, it's very hard to, well, it's not so hard. We also published papers on that, but it was kind of unexpected that the black holes that LIGO saw were as massive as they were. And so at the time, one of the windows for primordial black holes that was not ruled out by experiments was exactly around there, 30 solar masses or so. And so they published this paper saying, oh, maybe LIGO has not seen black holes that were made by dying stars. They were not the zombies that I was talking about before. They were primordial black holes that were formed from fluctuations in the early universe. And I think if you talk with Mark now, he will say, yeah, maybe, no, maybe not. But, you know, we'll keep looking. We'll keep looking, because if we find them, they will tell us a lot of interesting things about the early universe.
Other questions? Right there.
I just had, when you have...
Hold on, wait for the microphone so folks online can hear.
Sorry. When you have the triangle out in space, how will that be affected by solar winds?
So that's a very good question. So you have to shield all possible disturbances, okay? And that gives me an excuse to go back to one of the things that I got there. You see here, so that's a very valid concern. Anything out there is going to push on whatever is inside that satellite, in particular cosmic rays. You know, there's all sorts of things that can push on it. So this experiment was looked at with some suspicion, I think I can confidently say, for a while, because you have to show that you can keep stuff in free fall to a very, very high accuracy if you want to carry out the experiment I was talking about. So basically, the satellite is falling freely, like everything does happily in the universe when there's no ground to keep them up. And you want to make sure that it's falling freely to a very high accuracy. So you want to keep down the acceleration noise. That's what it's called. So basically what you do is you build a test mass that is what you want to make sure is falling freely as accurately as you need, and you shield it. Okay, you shield it from everything else. And so when anything passes by, say a cosmic ray hits the shield around that mass, you have sensors that push back so that that mass keeps freely falling. And you want to demonstrate that you can do it as precisely as you need. This is what that experiment did. And that experiment was launched the day my daughter was born. And so I told my wife, what about we call her Liz? And she said, you're insane. You're insane. We didn't.
What kind of shield do you use?
You don't use an actual shield. What you do is you have sensors that measure the disturbance on the outer shield, and you push back. And you have to do this very, very accurately. I'm not an experimentalist. Don't ask me these things.
It's an uncertainty how strong the solar winds will be.
Right. Yeah. Another reason why this thing is trailing behind the Earth is that the Earth is sweeping stuff away. So, you build it and it's following the Earth and it kind of...
All right, other questions? Right, over here.
Thank you. Do accretion disks form around black holes?
The accretion disks form when black holes, so you want to know why black holes have accretion disks. Okay, there's various different ways that black holes can have accretion disks. Many stars in the universe, very large fraction of the stars in the universe, in fact, are in binaries. Okay? So imagine that you have two stars. One star becomes old, runs out of fuel, collapses, forms a black hole. The other star is over there. The other star keeps expanding. When the star expands, it starts transferring mass to the companion. That's an accretion disk for you. So this is one way that a black hole can eat from another star. It can accrete matter from the star that is now becoming old. Okay? In fact, that process can become very complicated and it can create what is called a common envelope, but I will not go there. Supermassive black holes can eat in other ways because supermassive black holes are typically at the active center of galaxies. And there's a lot of stuff going on there because that's where gravity is the strongest and a lot of gas falls in. So each of the black holes in a galaxy is expected to have a lot of gas around it. And then one of the things that we want to understand with LISA is maybe when galaxies come together, each of these black holes is going to have an accretion disk around it because it's at the center of its own galaxy eating stuff. And when they come together, they could keep those accretion disks. So what happens to the two accretion disks as the two black holes come together? And that's going to be interesting because the black holes that we are seeing with LIGO, we think there's going to be very little gas left around them. And when they merge, astronomers don't get very excited because they do not expect fireworks to happen. But with the black holes that we're going to see with LISA, there's hope that we're going to see electromagnetic fireworks after they merge. So you'll have this gigantic splash of gravitational waves and then fireworks that follow. And that's going to be fun if I live to see it.
All right. Well, if there are no more questions, let's thank our speaker again. Okay, so next month, November 4th, Sarah Kendrew. And do we have the Maryland Space Grant Observatory? Yes, we have the Maryland Space Grant Observatory coming down here. If you would like to go across the street and look through the telescope, please join this gentleman here. And thank you, and we will see you next month.